Let's still work with tensor product. Let's work with tensor product of R linear maps and combine with extension. So our notation is as before. R is a ring. We have ring homomorphism from R to S. Make S in particular our module. And so we have base extension, extend scalar from R to S. So as we discussed, this turns R linear map into S linear just by tensor product of identity map with this R linear map. So more rigorously, actually the correct procedure should as follows. So basically what we have introduced is if you have two R linear maps, find C, then find tensor C is again R linear map. So here, more rigorously, we only know that this is an R linear, not S linear, because you can only, to use the fact mentioned, you tensor this R linear with another R linear, the identity map, although it's over S, although it's S linear, but it's also R linear. So in particular, this tensor product of two R linear gives you R linear. So why it's S linear? Because we check it. So actually we claim that this is S linear. Basically we have to check this finitely, right? And to check this, so why not put this as first part of the exercise? To check this, basically you only have to check this on elementary tensor. Because obviously this is additive map. So we check for any element small s tensor M. If you tensor is S prime, then this is by this module structure, this is S prime S tensor M. And then by the definition of tensor product of linear maps, this is just S prime S tensor phi of M. And so this is what we want to check is whether this is the same as S prime 1 tensor phi over S tensor M, which is S prime, then S phi M. Right, so with yes, so phi M is already M prime, so this is the S tensor M prime. Wait, this is S tensor phi M, and so this is again S prime S tensor phi. Okay, so they're indeed the same. So we will denote phi S, the just described S linear map 1 tensor phi, to remind us this is S linear. So in particular, phi phi s. It's from S tensor M to S tensor M prime. Small S tensor M is mapped to small S tensor phi M, right? Remark, notice one identity. Let's see. Identity tensor, identity of M. This is identity over whole ring. And if you compose two S linear map, then obviously this is again identity tensor is the composition. And by our new notation, this is just phi s compose phi prime s equals phi compose phi prime s. This is just saying identity ms equals this. Actually, this is saying, why do we discuss this? This is saying that the procedure of turning R modules and R linear maps to S modules and S linear maps let's say, let's be more precise. Is factorial. What is factorial? I think more precise what he's saying that R modules to S modules, the functor, we can construct a functor. This is a functor actually. It turns R linears into S linears. And the composition of R linears into composition of S linear. And the identity of R linears into identity of S linears. Right? Okay, so now let's step into the main topic. First exercise. Let's see how to use this to prove some results in creative algebra. Let R be a non-zero commutative ring. If the free R module has isomorphism as R module, then we claim M equals N. If there is a linear surjection Rn, then M is bigger or equal than N. Solution. Let M be a maximal ideal of R. This always exists by Zern lemma. And then you consider the tensor product. And we know that, so in general, more general, you have this, right? Recall. And so in particular, let me think, I think we also have, yeah, we also have very general. Let's say, how to write it general enough. Yeah, this is general enough, I think. We have this. And so, combine these two, you should already have R, M, direct sum with itself, and time is the same as direct sum with n time, right? And so, in particular, when you apply this, this tells you that R quotient and small m is isomorphic to R quotient by maximal ideal small n, but these are just fields. So the vector space. So vector space is isomorphism if and only if they have the same dimension. This tells you this is true. Similar reason, just because, as we know, tensor product base change turns surjective into surjective. Let me be more precise. So basically, we're talking about this identity tensor, your previous function phi, right? And so both are surjective. So I mean, if you have this, then call this phi, then the identity tensor, it will still be surjective this time, and right. So again, by the dimension argument, m bigger equal than n. Remark: we can't use similar argument to show a linear injection forces, because injectivity is not generally preserved by base change. Okay, so let's say one more exercise. This is exercise 3. Exercise 4. Let R be principal ideal domain. And let big M be a finitely generated R module. And we use structure theorem for principal for modules or principal ideal domain, finitely generated modules or principal ideal domain. It's very similar as happening groups. So there are free part and torsion parts. And there is a theorem telling us that you could rearrange the order such that it's not only rearrange the order, I mean, there is a unique way to write it into such a form and at the same time satisfying A1 divides A2 divides AK. And the exercise asks you to prove the integer d equals dimension of this K vector space. So if you remember the exercise we have done before, so this dimension is called the rank of M, and it corresponds nicely in this situation. So K is the fraction field of R, okay? Therefore, remark, so D is uniquely determined by M, and it makes sense to define the rank of the freeness of M. Okay, so it seems like if you put this therefore, I mean, maybe he's not assume we know the structure theorem of. He's just saying, the exercise is just saying that let M be a finite generated R module of this form, then we can use two of our tensor products to show that the free part has a unique rank. The solution is similar, so we use tensor product. Then what do we have? We have K tensor M for K as K vector space. On the left hand side is isomorphic to we'll say this is R, yes, is isomorphic to on the right hand side, k to the power d, because if there is torsion, then this is 0. We have proved this before. So this is whenever there is a k-vector space, you put it here, and then there is, if any element has finite order, then this is 0. Anyway, this is easy. Suppose you have x, and then you have some, let's say, small k, and then because this is a fraction of r, I can always use a trick to do this. This a comes from here, but because it's in r, I could move it to the left hand side, so this is 0. Okay. So finally, the most important part of today's exercise is the follows. So this is very important because firstly, you saw this many places. Secondly, this is looks related with what we discussed before. It's better to distinguish this. Let's first write it down. Let M prime be our modules. Then there is unique S linear map S tensor over R with R linear maps from M to M prime, map it to S linear maps descend small s tensor phi to S acting on phi s. So phi s is defined over here, right? And so it's a major fall into here. And so we just multiplying, and because this is S module. So as a map, this maps T to S phi S T. And it is an isomorphism if M and M prime, as you could expect it as before, finite free. Because when it's finite free, we can use the method of taking a basis. Our modules. So let's prove it. Firstly, let's construct this map. So it's about tensor product. So we construct firstly bilinear map, R bilinear map. One checks this is, let me just use light notation, sorry. You understand what it is. This is base change test. Okay, this is R bilinear. On the first position, this obviously is R linear. On the second position, By the construction of phi S is one tensor is phi, and so it's again R linear. And so it induces a map from the tensor product to the target. This is just R linear. Let's call it L. So L is R linear. By universal property of tensor product over R, but actually also S linear. So I left you to check it. Now let's use the condition. M and M prime have basis, finite free. Let's say AI is a basis. For M, the E J prime a basis for M prime. And in this case, by our results before, we know that so the target and the domain both become a free S mode, right? And we know that they have S basis for, so again, let me just use line notation MS and then prime S. So one basis could be given this. Respectively, one tensor is EI prime, EJ prime, sorry. Recall that the R basis of this free R module, we have described this before, is the function phi ij, which maps EI to EJ, EJ prime, sorry. And all the EK to 0, K different from I. Wow. S basis of S, MS, prime S, sorry, let's wait for a while. S basis for base change of this is just tensor product, right? Now let's look at the target of the basis element, the image of the basis element, sorry. So L of 1 tensor phi ij acting on basis element EI. What is this? By definition, this is phi ij EI. More rigorously, this is 1 tensor phi ij, and so this is 1 tensor ej prime by our definition of phi ij, and all others would be mapped to, obviously, to 0. Hence, this implies that L thins basis to a basis of home S, M, S, and prime S. So this is isomorphism.